Okay, so now we're moving on to the combined gas law. Before I get into that, just let me remind you, we talked about the definition of pressure, we talked about the units of pressure, we talked about that when we are dealing with a gas, that a gas occupies whatever volume you put it in. And remember how I told you guys in the last video that I could put all the gas molecules that are in this room into a Coke bottle. I finally got the right glasses and I found that it was 355 milliliters. So basically you can squish a whole bunch of molecules into that small space or let them roam around in this large room, and it's the exact same number of molecules. So we're talking about the volume of the container is the volume of the gas, okay? And then we also mentioned in the last video that anytime we're dealing with temperature, the temperature has to be in Kelvin. Okay, what is the combined gas law? Well, remember how we did Boyle's law, where temperature was held constant, and that was the relationship between pressure and volume. And then we did Charles' law, and we said that pressure is held constant, and that was the relationship between volume and the Kelvin temperature. Well, the combined gas law is that you combine both of those together, and everything changed. Nothing is held constant. So here is the combined gas law. P1V1 over T1 equals to P2V2 over T2. If you hide the temperature, mainly basically say hold that constant, there's Boyle's law. P1V1 equals to P2V2. If you hide the pressure, I don't know if you can see that with me being here. If you hide the pressure, does that work better? Not really. But anyway, if you hide the pressure, you see V1 over T1 equals to V2 over T2. So what you see in the combined gas law is both Boyle's and Charles, all right? So when do we use the combined gas law? When the temperature changes, the volume changes, and the pressure changes. For this problem that I put on the board, I made sure that I got two different pressure units and two different volume units, just to remind you that you have to make sure that on both sides of the equation you have the exact same units of volume and the exact same units of pressure. It doesn't matter what units they are. You could have torr for the pressure, or atmospheres for the pressure, or millimeters of mercury, or pascals. But the key thing is that you have to have the same units on both sides. And with the volume, if you're going to have milliliters on the left, you better have milliliters on the right. If you're going to have liters on the left, you better have liters on the right. And obviously temperature, Kelvin, all the way. Okay, so here's our little problem. A sample of methane gas occupies 260.0 milliliters at 32 degrees Celsius. So that means it's in a container that is 260 mils. 32 degrees Celsius under a pressure of 0.500 atmospheres. Okay, at what temperature would it occupy 0.500 liters, so half a liter, under a pressure of 120 millimeters of mercury? So notice what we have here. We have pressure in atmospheres and pressure in millimeters of mercury. So what we're going to need to do is convert one to the other. So you decide. You could either have both of them in atmospheres or both of them in millimeters of mercury. And also with the volume, you see here it's in milliliters and here it's in liters. So you've got to convert one to the other. Okay, so let's go ahead and do the problem together. Let me just put some organized stuff here. Not organize it here. I'm going to say, all right, what is the initial pressure? P1 is 0.5 atmospheres, 0.500 atmospheres. What is P2? P2 is 120 millimeters of mercury. So you decide, which one are you going to do? Again, obviously, you're not talking back, so I'm just going to decide myself. So I'm going to go ahead and convert this to atmospheres. I don't have to. I can convert this to millimeters of mercury, but I'm going to convert this to atmospheres. How do I do that? I go 1 atmosphere is 760 millimeters of mercury. That's my conversion factor that we learned in intro chem and also in the first video. All right, so I'm going to go 120 divided by 760, and I get 0.158 atmospheres to 3 sig figs. So 0.158 atmospheres. Okay, so that's my P2. All right, now V1 is 260 milliliters. 260 milliliters. V2 is 0.500 liters. All right, so if this is 0.5 liters and this is 260 milliliters, I have to convert one to the other. I'm going to go ahead and convert the milliliters to liters. So what I'm going to do is I'm going to move the decimal place 3 places to convert my 260 to 0.2600 liters. Okay, so this is liters, liters, atmospheres, atmospheres. I'm good. I have T1 is 32 degrees Celsius. What do I have to do? I have to add 273 in order to convert that to Kelvin. So 2 plus 3 is 5, 3 plus 7 is 10, so 305 Kelvin. And T2 is my unknown. That's what I'm looking for. All right, so now it's just a matter of plug and chug. You plug it into, I'm going to erase the actual problem. Hopefully you've already written it down in your notes to get rid of the clutter. I know this board always looks way too cluttered. Remember, it's P1V1 over T1 equals to P2V2 over T2. So I'm going to put 0.500 atmospheres, and then V1 is 0.2600 liters over 305 Kelvin is equal to 0.158 atmospheres, 0.500 liters, and this, my T2, is my X. That's my unknown. So anytime you have an unknown in the denominator, you guys should know this already because you're way beyond the simple math abilities. You cross multiply to get a linear equation, and then just make sure that that unknown stays in the numerator. So I'm going to say T2 is equal to, basically I bring this up here, bring this over here, bring this down here. So it's going to be equal to 0.158 and then 0.500 and then 305. And then down here, this guy's going to be 0.500 and then 0.2600. Now, if I put the units in there, you will see how everything cancels. So this would be atmospheres. This one over here is liters. This one is Kelvin. This one here is atmospheres. And this one's liters. So look, the liters cancel, the atmospheres cancel, and you end up with Kelvin in the numerator. Usually with these problems, once you get your final temperature in Kelvin, you have to then also switch it over to Celsius, because most of the time with exams, the question and homework, they ask you for your final answer in Celsius. So don't forget to convert the Kelvin to Celsius. So plugging it into our calculator, 0.158 times 0.5 times 305 divided by 0.5 divided by 0.260 equals 185 Kelvin. So T2 is equal to 185 Kelvin. What if I want it in Celsius? I'm going to subtract 273, and I end up with minus 88 degrees Celsius. because what you end up with is minus 87.65 rounded up, because you want no decimal places. Anyway, so this is your final answer here. Let's see. Hopefully you can see that. Okay, good. So that's the combined gas law. Let me give you guys an introduction to the ideal gas law, and then in the next video, we'll do a problem with the ideal gas law, and then we'll do applications of the ideal gas law, because this is not intro chem anymore. This is Gen Chem 1, which is college chemistry. The intro chem, which a lot of you took 1050, that's more of an introduction to general chemistry. So what we're going to do is not just plug and chug the ideal gas law. We're going to learn how to do that, and then we're going to use it to figure out molecular weight of an unknown compound and density of a compound. Again, but that'll be in the next video. What is the ideal gas law? The ideal gas law is PV equals nRT. This is the ideal gas law. Ideal gas law. Okay, what do we use it for, and what does everything stand for? Well, anytime you want to know about a quantity of a gas, this N, this stands for moles. So you can figure out how many moles of gas you have in a container if you know the volume of the container, if you know the pressure of the gas, and you know the temperature. And using this universal gas constant, you can figure out the number of moles. And if you know the identity of the gas, you can then figure out how many grams you've got. So we can use it in stoichiometry problems, and you'll see a whole bunch of applications other than that. Like I said a little earlier, you can figure out molecular weight of a gas, you can figure out density. Okay, R is the universal gas constant. Universal gas constant. Now, there are many different values of R. So it depends on the units that you're using for pressure, volume, and that will determine the R value that you're going to use. In general, I tend to use the typical R value that you probably learned in intro chem, R being 0.082, sorry, give myself some space here. R is equal to 0.0821 atmospheres liter over mole Kelvin. So what this is telling me is that I have to have my pressure in atmospheres, my volume has to be in liters. Obviously this is moles, and we already know that temperature must always be in Kelvin. Okay, so if you are going to use this R value, make sure you have your pressure in atmosphere, volume in liters. If you use a different R value, they have R values where they use millimeters of mercury and they use milliliters. So again, depending on which R value you're comfortable with, this is the one I tend to use. Okay, so in the next video, we will do some ideal gas law problems.